Swayam Prabha. Digital India. Educated India.
Welcome to another lecture on control systems. So as with the last lecture or so, we will continue to see more details about this topic called Bode plots. Okay. So we have seen that this Bode plot is basically a frequency domain tool, and it can do essentially the same things that a root locus can, in the sense that it allows us to design controllers or compensators to meet certain performance objectives for a control system, right. So we started to look at some of these building blocks of the transfer function from the perspective of drawing or sketching the asymptotic Bode plots. We also saw that you can refine those asymptotic Bode plots to get a reasonably nice smoothened version of the Bode plot, right. What we need is basically a semi-log paper. So this is to refresh what we did last day, what we talked about. We have to have a semi-log graph paper in which the independent variables axis, that is the x-axis, was on the log scale, right. So it was a logarithmic separation between successive grid points, which is to say that between every successive two successive grid points there was basically a scaling of by a factor of 10, right. On the y-axis, which is the dependent variables axis, however, we had a linear scale because we were taking the log of the magnitude and reading off the units in decibels. We also saw why it's called decibels and not bells, and we also saw why we have this factor of 20 multiplying this log of the magnitude function, right. Okay, so we'd already seen furthermore that what the Bode plot for an integrator or a differentiator block looks like. We've also seen how the Bode plot for first order terms, that is real poles and zeros, look like. Now today we'll start by looking at what these Bode plots for the second order blocks, what they happen to look like. Okay, so let me just quickly refresh your memory. Here is what we have already seen. So today we are going to start off by looking at this particular block, which is basically a pair of complex conjugate poles or zeros. So if it's a plus here, plus 1 here, it's a 0. If it's a minus 1 here, it's a pole. Okay, so this is what is going to be at the focus of our attention in this lecture, right. So without further ado, let me get about to drawing this. So here's what we have. It's j omega over omega n squared plus 2 zeta omega over omega n plus 1, right, to the power plus minus 1. We saw that in order to sketch the Bode plot, this is the standard form in which we pull out. So in other words, we divide everything out by omega n squared, right, and then this is the form that we get, all right. So if that is so, then how do we go about sketching this magnitude function for this, all right. So the magnitude function for this would be, of course, you can see that this is j omega, so when it's squared it becomes real, j squared is minus 1. So then this minus omega over omega n whole squared will team up with this 1 to give you the real part. Of course I forgot the j here, right. So then we have 1 minus omega upon omega n squared is the real part, right, plus 2 zeta omega over omega n is the imaginary part squared, and then we take the square root of this whole thing, right. So this is going to give us the magnitude function, and what we are interested in sketching is this 20 log m omega. So as in all the previous cases, yeah, we would do well to actually split this case up into 3 particular scenarios. One, suppose omega over omega n is much less than unity, yeah. In that case we can ignore this term here, right. So we can ignore this term here, and we can also ignore this term here. So then m omega is almost close to unity. So therefore 20 log of m omega can be approximated by the 0 dB constant line, right. So of course I should probably put a plus minus 1 here, yeah, depending on whether it's a 0 or a pole respectively, right. Okay. Now next we consider what happens at omega is equal to omega n. At omega by omega n equal to 1, we have of course this entire thing vanishing. So basically the real part vanishes. So we have m omega given by 2 zeta to the power plus minus 1. And you immediately begin to see that something interesting happens, because this is a second order system and you have 2 parameters to sort of uniquely identify a second order factor. One is the zeta, the other is the omega n. You see, earlier when we were talking about these first order factors, we were only talking about the time constant, and that sufficed. But now there are 2 things to play around with, both the omega n as well as the zeta. But we have so far not even considered this zeta, or how this m omega plot varies, or this 20 log m omega plot varies as a function of zeta. We will see that very soon. But for now let us just quickly wind up this with a third observation, which is when let us say omega over omega n is much greater than unity. So let omega over omega n be much greater than unity. So here what is going to happen is, you see this 1 is hardly comparable with this omega over omega n whole squared. So this term is clearly going to be predominant here. The other thing is, of course, when you have a very large number, so for x very large, so again let me write that down as a separate observation. If you have x squared plus alpha x plus beta is almost approximated by x squared. The highest degree term, if it's a polynomial, then the highest degree term in a very large, in this x is going to be a very good approximation, yeah, because this is probably going to be, so for example take x to be 10 to the power 6, right, then x squared is of the order of 10 to the power 12. And you see alpha times x, if alpha and beta are not unreasonably high, so if alpha and beta are relatively of smaller orders, then alpha x is also of the order of x. And even if alpha is very large, you can always find a particular range of x. So if alpha is of the order of 10 to the power 12 or 10 to the power 6 as well, then consider x to be of the order of 10 to the power 40, for example. Then if x is of the order of 10 to the power 40, x squared is of the order 10 to the power 80, and even if alpha is of the order of 10 to the power 6, you see alpha x is of the order of 10 to the power 46. So 10 to the power 46 and 10 to the power 80, both are large numbers, but of course you can immediately see that 10 to the power 80 is way larger than 10 to the power 46. So the basic idea is that this highest degree term will be a very good approximation as x goes to infinity, yeah, which is essentially what we are trying to analyze here, because we are trying to draw up for this asymptotes, remember. So therefore we will say that this entire term is now predominantly this omega squared upon omega n squared is equal to m omega. So therefore if you take the log of this, yeah, so this of course to the power plus minus 1, let me not forget that, yeah, of course this is also, yeah, so we are fine here, yeah, so we have plus minus 1. So this obviously, let me complete the story here, so 20 log of m omega is equal to 2 zeta to the power plus minus 1. So, if it is a 0, it is a 2 zeta, if it is a pole, it is minus 2 zeta, sorry 1 by 2 zeta. Yeah. Now, let us look at this. So, therefore, 20 log of omega squared upon omega n squared, of course, this will be plus minus. Yeah, this is going to be 20 log of m omega is equal to, it is going to be this. So, now I can pull out this squared factor here outside the logarithm. So, this becomes plus minus 40 log of omega upon omega n, right. So, what I then see is that at very high values of frequency, the slope of the line will be plus minus 40 dB per decade, which is to say that if you take omega is equal to omega n, then it is obviously 0 dB. So, the high frequency and the low frequency asymptote. So, remember this was your low frequency asymptote and this is the high frequency asymptote. So, this is low frequency asymptote, this is the high frequency asymptote, as in case of the second or in the case of the first order factor. Here also we see that at omega is equal to omega n, yeah, if you take omega is equal to omega n, you can see that you go either way, this high frequency and low frequency asymptotes will intersect. Of course, we know the exact value at omega is equal to omega n, which is this plus this is 2 zeta to the power plus minus 1. But if you just forget about this point for the time being and you just focus on the low frequency asymptote and the high frequency asymptote, the low frequency asymptote is a constant flat line at 0 dB. The high frequency asymptote on the other hand is a line that rises or falls at a rate with a slope of plus minus 40 dB per decade, yeah, and at omega is equal to omega n, of course, the high frequency asymptote is also 0 dB, right. So, it looks like we can roughly sort of sketch this. This is 20 log of m omega. So, it would seem like if this is the, say, the 0 dB line here, this is the 0 dB constant line here, then it would seem like there is no difference between this second order, or rather this complex, the system with complex poles and zeros, yeah, the Bode plot of the system with complex poles and zeros, and that of the system that we have seen for the first order poles and zeros, except for the fact that there at the corner frequency, so let us say this is the omega y omega n axis. So, here you have this 1, here you have this 0.1, here you have this 10 suppose, right. So, the only difference that happens in this case, it would seem like, is it would go flat up until omega over omega n is equal to 1, and then for plus 1 it would rise. So, let me mark out, this is 40 dB and let us say this is minus 40 dB excuse me. So, at 10 times this value, that is at 1 decade above this so called break frequency or corner frequency, which is omega n in this case, what we have then is a line like this, which is now descending at minus 40 dB per decade. This is for the pole, and which would rise at plus 40 dB per decade for a 0, and it would seem like we are okay, right. There is nothing more to be investigated in this, but remember, as I mentioned, so this zeta plays an important factor here too, right. So, earlier at the corner frequency we saw that it was square root of 2, so we had this 3 dB correction that we introduced, but now you see we have this exact value at the so called break frequency or corner frequency in this case, that is omega is equal to omega n, and we have the exact value here to be a function of zeta. So, you cannot just give it a blanket statement that this is going to be such and such value, right, it will depend heavily on zeta. Moreover, if you now study this magnitude function a little closely, so let me write that down once again, this is 1 minus omega squared by omega n squared whole squared plus 2 zeta omega over omega n whole squared, right. So, now the problem is, and I leave this to you as an exercise to check that m omega, okay, let me just put that plus minus 1 sign as well, m omega will have an extrema, by which I mean it could be a minima or a maxima. So m omega will have an extrema at omega is equal to omega n times 1 minus 2 zeta squared, yeah, and the value of the extrema would be 2 zeta times 1 minus zeta squared to the power plus minus 1, depending on whether it is a pole or a 0, alright. So, I leave it to you as an exercise. It is not really difficult. You see, the first thing that you need to get rid of is the square root, because obviously if m omega has a maxima or a minima, so does m omega, this square of this m omega, right. So, then you basically need to differentiate. So, the hint, I am not going to really solve this, the hint is that you differentiate d omega of m omega squared, yeah, and equate it to 0. Of course, if you want to check whether it is a maxima or a minimum, you have to do the second derivative condition. So, you equate this and solve for this. It will be after all a polynomial equation, and you will see that this maxima occurs. So, this will give you root at omega n times square root of 1 minus 2 zeta squared, okay. That will be the feasible solution, okay. And then if you plug in that value, of course, then it is pretty straightforward. You just plug in this value here. The second part is pretty obvious. So, you see this omega n squared comes here, then this 1 minus 2 zeta squared. So, this omega n squared would cancel out. So, this is just 1 minus 2 zeta squared. So, 1 minus 1 plus 2 zeta squared. So, this is going to be just 4 zeta squared, 4 zeta to the power 4, right. And what about this? By the same token, you will have this 1 minus 2 zeta squared times 2 zeta times 4 zeta squared. So, you put this all together and you will see that this is what you eventually end up with, okay. So, I leave that to you as an exercise. It is not really difficult. All that you need to do is carefully take the derivative, and this is not a very complicated function as such for differentiation, right, straightforward that way, and then you solve for this. So, this is the result that you get. The reason why I am actually interested in sort of stating this result, even though I am not solving this or actually showing you the so called proof of this, which I left as an exercise, is that notice this value of omega at omega n times square root of 1 minus 2 zeta squared will not exist, yeah, for every value of zeta. So, let me make the first observation here. So, the observation is that the extrema does not exist for every value of zeta. It will only exist if zeta is less than 1 by square root of 2, less than or equal to 1 by square root of 2, right. Why? Because this, remember, this term inside this radical, this 1 minus 2 zeta squared must be positive in order for this to be a real number. So, therefore, this dictates that 1 minus 2 zeta squared must be greater than 0. In other words, zeta should be less than 1 by root 2, which we obviously approximate as 0.707 if I am not mistaken. So, unlike in the case of the time domain thing where you saw this peak overshoot, the reason I am drawing a parallel is, you see, we have to have now performance metrics defined in terms of frequency domain parameters. Earlier, when we were studying this time domain characteristics, we studied these performance metrics in terms of step responses, and we had this peak overshoot corresponding to a step response, the percentage overshoot. We saw that the percentage overshoot was a function of zeta. Interestingly, when we are now looking at the frequency domain plot, these are two different objects altogether, but you see whether this particular plot of magnitude of this log magnitude plot will have a peak or not. So, for example, if there will be a peak like this, or there will be a say for example a trough like this, yeah, that will be determined, it seems, as if by the same parameter zeta. So in other words, in the time domain, a way of specifying zeta indirectly by visible parameters is percentage overshoot is something that even a lay person can see by looking at a step response. So a lay person can just tell you, okay, this is the percentage overshoot that is acceptable. Immediately a control engineer will translate it to some constraints on zeta. Similarly, if you just show this frequency response plot to a reasonably, not a very absolute lay person, someone who understands frequency response but doesn't know about all the nitty-gritties. So that person might say, okay, this is the kind of peak or trough that happens at this frequency, which I am not particularly fond of. So I want this to be restricted within this band. You see, immediately that also translates to a constraint on zeta, right? So we have a grip over this performance even in the frequency domain, which translates to some restrictions on zeta, okay. So therefore, the point that I am trying to make here is that although these are very similar, there is one subtle crucial difference. In the time domain case, what we were mostly concerned with was this zeta, the critical point zeta is equal to 1. Yeah, so if zeta is equal to 1, we said it's a critically damped system. If zeta is less than 1, yeah, then we called it an underdamped system. If zeta was greater than 1, we called it an overdamped system, right? But here in this case, it seems that zeta is equal to 1 does not play that significant a role. Instead, that mantle is now taken over by this value of 1 over root 2, which is 0.707. So if zeta is less than 0.707, then you will have this peak phenomena in the frequency response plot of a second order factor, yeah, or a trough if it's a 0. On the other hand, if zeta has damping greater than 0.707, it may still be underdamped. In other words, if it's underdamped, it means there is still a complex pair of poles or complex pair of zeros, right? But still, you will not have this peak. Now it turns out that this peak also has a name. Just like the peak in the time domain case, we called it a percentage overshoot. Here, this particular peak has got a name and it's called a resonant peak. Yeah, let me repeat that term, a resonant peak. So again, why are we interested in this? Just like we specified some performance metrics in terms of time domain characteristics or time domain features, now we are interested in specifying those same characteristics in terms of, or like similar characteristics in terms of frequency domain specifications, right? And for that, the important term here is this MR, okay, which is called this resonant peak. So now, as I said, in our course here, we will not really get into details of designing a controller or synthesizing a controller using this frequency domain response. But at least having done this course on control systems, it is imperative that you as a student should be aware of these different terms, right? So if someone specifies performance metrics in terms of time domain features, it immediately registers in your mind as to what it entails in terms of those zeta, omega n, etc. Similarly, if someone translates some performance metrics in terms of frequency domain terms like resonant peak, like bandwidth, yeah, and so on and so forth, phase margin, gain margin, and these things that you might often have heard earlier, after doing this course and especially studying this Bode plot and later on what we will study as Nyquist, yeah, you should at least have a very thorough idea about what it means, right? That is the perspective we will take on this topic, right? So now you see this MR, yeah, is nothing but this. Okay, so this is the resonant peak. So in other words, let me just draw this for a pole, an example pole here, suppose. So you have, for example, the asymptotic approximation of a pole is say like this is decaying at minus 40 dB per decade. But now if you want to draw the exact thing here, you will see that you will have to account for this. Where does this peak occur, by the way? So notice, that's another interesting thing here. So notice that this is at omega over omega n, this is at unity. So this is basically at omega is equal to omega n, you have this break frequency. But where does this peak occur? See, the peak occurs before the break point, that is omega n. Here omega by omega n is clearly less than 1, no, at this point. So therefore this peak occurs before the break frequency. So if I am to draw this for the pole, and you can draw this similarly for the 0, right, it's just the other way around, so there will be a trough. So here you will see, if I want to draw this accurately, it will probably look something like this, sorry, it will not deviate from that line, there is no reason to deviate from that line. Let me be a little more careful here. Yeah, and then it merges and sticks to this black line and goes like this. Now, the other thing that I am going to ask is, let us see what happens to this peak as zeta changes. So, of course, we have seen that if zeta is greater than 1 by root 2, then this question of this peak does not arise, because this extrema point itself does not exist, that frequency. But suppose zeta is less than 1 by root 2. So, there is still a wide range of zeta to choose from 0 to 1 by root 2. So, 0 to 0.707. So, within this value 0 to 0.707, what happens? Suppose you start with zeta is equal to 0.7 and you keep reducing zeta. One of the things we notice is that as you keep reducing zeta, this omega by omega n increases. So, as zeta reduces, the location of MR, so let me point it out here what this MR is. So, if this is your 0 dB line, then this is the MR, this is the resonant peak. So, the location of MR, that is the frequency at which this MR occurs, which is obviously before this omega n, yeah, shifts closer to omega n, that is shifts to the right, yeah. So, that is an important observation. What about the other observation, that is what happens to the value? So, does this peak increase or decrease as zeta changes? So, for example, if you choose zeta to be very small, yeah, so in this case, of course, if we choose zeta to be very small, what will happen? So, if we are drawing the pole, for example, then we will take the tau to the power minus 1. So, if zeta decreases, then what happens? This value increases, but this value decreases much more. Yeah, so I put it to you to check that if you check this out, yeah, how this peak value, how this is affected, yeah. So, if you reduce zeta from 0.7 to let us say 0.1, so what happens to this value at 0.1? This is 1 minus 0.1 squared, that is almost 1 minus 0.01, this is almost equal to 1. So, you see this factor 1 minus zeta squared under root does not change too much, yeah. If you choose, for example, zeta is equal to 1 by root 2, which is the critical value, yeah, beyond 1 by root 2, if you increase zeta beyond 1 by root 2, as we have seen, no peak or trough exists. So, at 1 by root 2, what is this? This is half, so 1 minus half under root, so that is square root of half, so that is 0.707, and at zeta is equal to 0, this is 1. So, the entire range of zeta over which the peak exists, that is from 0 to 0.707, this factor, yeah, this factor changes just from 1 to 0.707. So, it has just a change of 0.3. On the other hand, this factor, if you look, as you keep changing zeta from 0 to 0.707, of course, you cannot make it exactly 0, otherwise this will be undefined. So, maybe the open interval 0 to, so we are interested in the variation between the open interval from 0 to 0.707. So, if you look at how this factor changes within this range, you see that there is a huge change, no? At close to 0, it can take almost infinite values, yeah, and at close to this, it settles for something like root 1 by root 2, yeah. So, rather if you put zeta is equal to 1 by root 2 here, then this is root 2. So, of course, if we take the minus 1 part, then this is 1 by root. So, this is root 2. So, it starts from at zeta is equal to 0.707, it starts from a value of root 2, this factor that I am circling by a red here, and as zeta goes to small and small values, it almost tends to infinity. So, this varies much more widely. So, I am saying that this is the determining factor, this factor does not change much after all, yeah. So, this factor only varies between, as I showed, this factor varies between 1 and as this is zeta is 1 by root 2, this is half, so 1 minus half square root, so it is 0.707, yeah. So, at zeta is equal to 0, this is 1, at zeta is equal to 0.707, this is also 0.707. On the other hand, this factor changes as zeta is equal to 0, this is almost like infinity, and at zeta is equal to this is 1 by root 2, so that's root 2, so it is 1.414. Yeah. Of course, this is not the way you generally write an interval. Yeah. So, oh, this is root 2, sorry, I am sorry. So, this, if you take this 1 by 2 zeta, if you take this to be 1 by 2 zeta, so because this is going to being taken with the minus 1's power. So, 1 by 2 zeta belongs to this interval. At zeta is equal to 0, this is almost infinity. So, of course, I am reversing the order here, this is not how you write an interval, right, and at zeta is equal to root 1 by root 2, this is again 1 by root 2. So, this has a much wider range as you vary zeta within this domain from 0 to, so this is where zeta comes from. So, as zeta varies from 0 to 0.707, you see this factor does not change much, but this factor is the one that changes the most. So, this is the determining factor. In other words, if zeta decreases, then the peak increases, if zeta increases, then the peak decreases. This is almost the same understanding that we had for, of course, they are two different objects, so we should not compare like this, but it is almost the same understanding we had for this time domain percentage overshoot, right. If we increase damping, the percentage overshoot decreased, if we decrease damping, the percentage overshoot increased. Here also we see that the resonant peak increases as zeta decreases and resonant peak decreases as zeta increases. There is another way of seeing this, if this sort of an understanding or analysis is not very appealing to you. So, here is what I am going to present next. So, think of this 2D plane here, yeah, we are familiar with this. So, this is the r axis, this is the JR axis, so the real and imaginary, yeah, we have already seen this. Now, suppose there are some poles and zeros, so this is a reason why I am drawing this in this sort of a flattened out version, I am not really drawing. So, this is after all a right angle, yeah, I am just drawing it in this fashion like as if it is drawn on the floor, yeah. So, suppose there are certain poles and some zeros here and some other pole here and so on and so forth, right. Now, look at the complex pole pair. Okay, let me just focus on the complex pole pair rather than bringing in all factors here, because here we are after all studying only the effect of this complex pole pair, no. So, we have this complex pole pair only. So, let us just focus our attention on this. Now, the reason I have drawn it flattened out in this fashion is because I want to do something very specific with this. You see, what is this Bode plot after all? If you look at this, yeah, it is basically that JR axis, right. So, we are taking this omega, it is as if this omega axis and this JR axis they are the same, it is either you call it the omega or the JR axis, and we are basically studying. So, essentially it is as if we are viewing it from this side. So, this is where we are the viewers. So, try to understand this is what I am claiming here. See, earlier in root locus case we were drawing this JR and this R, this plane, and we were sort of looking at it in this fashion. So, what we were looking at was this R and this JR, and you had this complex pole pair here. But now I am saying let me just flatten it out on the floor, and let us call this axis, this third axis, which is again perpendicular or orthogonal to both of these other axes, yeah. So, this is orthogonal to both of these axes, okay. So, this axis now is my 20 log of m omega axis. So, let me redraw that again in a larger version here. So, this is the R, this is the JR, and this is where we are viewing it from. So, this is where our eyes are, yeah, this is our eyes. So, we are the viewer here, yeah. So, this is what we are looking at, and this is basically the 20 log of m omega, right, okay. Now, the point here we are trying to make is, yeah, that suppose you extended this in this direction, of course, and these are your like your omega axis going in this direction. So, what we are seeing is that this simple plot here would look something like this, and then it would go down at 40 dB per decade like this, yeah. So, it is as if we are just scanning along this 20 log m omega and JR plane. So this is like the x, y, z. So this is like the YZ plane. Yeah, so this YZ plane is what we are viewing. That is the 2D Bode plot that we are seeing, right? So what I wonder is this, what is this plot telling me actually? So suppose I had a pole pair here, yeah, what is this function at the end of the day after all? This function is nothing but if at that particular omega, so this is my omega, so at that particular omega I am just finding out it's a distance function, no? If you just think of it about a moment, for a moment, what is this? This is just the distance function. So if it's a pole, it's the reciprocal of that distance that I am taking. So it's a reciprocal of that distance. Yeah. So please try and follow this. What I am saying is that this is the pole pair here on the R and the JR plane, and now I am drawing a third axis which is going to be my function, this 20 log m omega function. So what I am saying is that this, in other words, the further that this pole gets from me, the larger is this distance, and the reciprocal of this distance is smaller. Yeah, and you can see that here also. So look at this function here, omega over omega n whole square plus 2j zeta omega over omega n plus 1. So if you take this magnitude function, let me write the magnitude function in one shot itself. Yeah, so this is 1 minus this times whole squared plus this whole squared, of course taking the j out. So this is what our function is. But what is this function? You see, this function is nothing but, it's basically telling me what the distance of this. So this point is what? This point is, according to my notation here, this point is nothing but this omega point here, no? So that is the omega I am plugging in here. Yeah. So that is the omega I am plugging in here. Of course, there is a scaling, a constant scaling by omega n of this distance function. But at the end of the day, you see, if this pole moves further away, of course this is to the power minus 1 for a pole. So this is for a pole, this is to the power minus 1. Yeah, that is what my m omega is, right. So the point is that as the pole gets further and further from this imaginary axis, yeah, it has a smaller and smaller magnitude when evaluated at this point. After all, this is nothing but the length of this phasor joining the pole, the complex pole, with this particular point on the j omega axis. That is what the Bode plot is, that is what the 2D Bode plot is. So it seems that I am only interested in this JR axis because I said that this is steady state analysis that is concerning us. Now, with this in mind, let us take a relook at how this zeta affects this value of this peak. Yeah. So for example, if you vary zeta, how does this pole location change? If you keep omega n the same, but if you are varying zeta, all that it changes is this radial vector, this radial phasor, its angle here changes. So if you increase zeta, so this is as zeta increases, you see this line joining this complex pole to the origin here, this rotates in the counterclockwise direction as zeta increases. And as this line rotates in the counterclockwise direction, this line has a constant length because omega n is fixed, omega n is fixed. So as you keep increasing zeta, this line rotates in a counterclockwise direction in this fashion, and as it rotates in a counterclockwise direction, you see its distance from the imaginary axis increases. And the explanation that I have just given is, as the distance from the imaginary axis increases, what impact does it have on the magnitude of this function, on this magnitude function? Because remember, there is a to the power minus 1 here. Yeah. So because of this to the power minus 1 that we have here, right, as the distance increases, this value decreases. Yeah. So at omega, at zeta is equal to like 1 by root 2, it is a 45-degree angle, right. So it is equidistant from the r axis and the j omega axis, the jr axis, and at that point this peak value here stops appearing. Yeah. So this was the peak. So this is what we are viewing. As a viewer, we are viewing this YZ plane is our 2D Bode plot that we have been seeing so far, right. So now as you keep increasing zeta, this rotates in this fashion, it gets further and further away from the j omega axis. As it gets further and further away from the j omega axis, the length of the line joining a point on the j omega axis and this particular pole, this complex pole, increases. As this length increases, this function inside this radical and with the radical indeed increases, but because it is the reciprocal, because it is a pole, so that value decreases. So this peak comes down, right. So this peak comes down and eventually there ceases to be a peak beyond zeta is equal to 1 by root 2 if you keep increasing zeta further. So I hope that that geometric interpretation at least appears more convincing to you than the argument I was making a while back about this function of 2 zeta into square root of 1 minus zeta squared. So this is also another way of convincing yourself, alright. So hopefully we have at least managed to show you that this is how it varies. But we haven't discussed one very important aspect so far, right. We have been only discussing this magnitude function. What about the phase plot? You see, a Bode plot can be specified not by the magnitude function alone, you also need a phase plot, right. So what about the phase function? Let us again write down that factor. So this is omega over omega n squared minus 2j zeta omega over omega n plus 1, yeah. So what is the phase of this? So the phase function of this will look something like, of course this is a plus minus 1, so I better have a plus minus 1 here also. Even if I forget to put this plus minus 1 at times, please remember that you will always have to put this plus minus 1, the plus corresponding to the 0, the minus corresponding to the pole. So now what we have here is 2 zeta omega upon omega n, the imaginary part divided by the real part, yeah. So this is of course the j omega, lest I forget. So this is 1 minus omega squared upon omega n squared, yeah. So again as before, if omega n is if omega upon omega n is much less than unity, so you can treat the denominator as unity itself, and you know it's just 2 zeta omega upon omega n, this is almost 0. So obviously phi omega can be approximated by 0 degrees. Similarly, if omega upon omega n, yeah, is much greater than unity, then this denominator is just omega. So then let me just write that down. So phi omega is equal to plus minus tan inverse 2 zeta omega upon omega n, and denominator will have omega squared upon omega n squared, right. Yeah. So we will then have something that, yeah. So we will then have something like, you know, if it's this is omega upon omega n. So if this is much greater than unity, as this tends to infinity sort of, what you then have is okay, let me retain this term for now. So this is 1 minus omega squared. So let us say omega is much greater than this. So what I will do is I will divide by omega squared above and below. That is what we do, right, when omega tends to infinity. So we will have this 2 zeta upon omega n, of course with a plus minus tan inverse sitting ahead of it, yeah, and this is like 1 by omega squared minus 1 by omega n squared, right. Yeah. So you see that as omega tends to infinity, this term goes to 0, this term goes to 0. So we will be left with only this minus sign here, right. we will be left with this minus 1 by omega n squared here, which is a constant number. So, I better this is almost equal to then plus minus tan inverse 2 zeta. So, this omega n squared will go up. So, it will become omega n upon omega, right, of course with a minus sign, right. So, you see the minus sign, it is very important to note where this minus sign is. So, the minus sign is basically in the real part, yeah. So, if the real part is negative and the imaginary part is almost 0, we know that it is at 180 degrees, right. So, it is either going to be plus 180 degrees or it is going to be minus 180 degrees, but the two of them do not make much of a difference, no. So, what I am basically saying is that this plot, again as with the first order factor here, if we draw this plot here, let us say this is the 0 degree line here, we will see that the low frequency asymptote is which is, let me draw with the blue here, yeah. So, you draw this low frequency asymptote, again this is omega upon omega n, yeah. So, this is unity. So, you draw the low frequency asymptote until here, or maybe 1 decade before this, or whatever corrections you want to make, but we will get to that shortly. It is getting more and more interesting here. And the high frequency asymptote, you see that for the 0, so this is for a 0 and this is for a pole, these will appear at either 180 degrees or minus 180 degrees, right. You can just analyze this function and you will find that this is indeed what the case is, right, yeah. Because as I said, you see as omega tends to infinity, this it is this denominator part which is basically the real part is negative, yeah, the real part is negative and the imaginary part is positive. So, that means it is on the negative real axis, and if it is a negative real axis, the phase is plus 180 or minus 180, but you have the plus or minus sign sitting outside. So, for the 0 it will be plus 180 and for the pole it will be minus 180. Now, of course, at omega is equal to omega n, things start getting interesting, because then you see the numerator is not a 0 quantity, but the denominator goes to 0. So, then at omega tending to omega n, phi omega tends to plus minus pi by 2, depending on which sign you are taking, whether this plus sign. So, the plus is for a 0 and the minus is for a pole. So, clearly in the asymptotes we have a discontinuity here, but at least we know that this takes an exact value of plus pi by 2 for the 0 and minus pi by 2 for the pole. But the question that we need to really focus our attention on and try and understand is this. Now, look, how is this? In this first order case we already saw, right, in the first order case, for instance, we had seen this plot. It goes from so if this is the 0 degree line and this is the minus 90 and this is the plus 90. So, these were first order factors. So, for the first order case we saw that, you know, at the break frequency it transition like this, yeah. So, you draw this sort of an asymptote and it went like this, or if it were a pole it went like this, yeah. So, you draw this, again you draw this. So, this straight line, this corner, this was giving you the asymptotic plot, and let me draw it with a different color. So, this is going to give you the exact phase plot or the better smoothened out phase plot, and this is going to give you the smoothened out phase plot for the 0. But now, for the second order factor, we have another parameter that should affect this, no? We have not even accounted for this zeta. So, we wonder what the role of this zeta is, right. So, now for example, we have this is the 0 degree line, this is the 180 degree line, and this is the minus 180 degree line, right, and we know that this is, let us say, 1. So, when our axis is omega by omega n. So, in other words, this is omega is equal to omega n, this point, right. So, we draw this low frequency asymptote until this point here, and then the high frequency asymptote from here. Of course, as I said in the previous lecture, we can go 1 decade lower here and 1 decade higher here, and in between joined by a slanted straight line, or you can go half a decade. It's a matter of taste, but really, as we shall see later, it really doesn't matter which way you go. Ultimately, it's an approximate plot. So here there's a discontinuity, as we encountered in case of the first order factor. The phase, about the phase plot, we are not so lucky that the high frequency and the low frequency asymptotes actually intersect. There is a discontinuity at the break frequency. So now we wonder how zeta, so far we haven't even factored the zeta in our consideration, right. So we now wonder, we are now left to wonder as to how this is going to blend in. So is it going to, for instance, let me use a different color. So is it, for instance, going to blend in like it did for the first order factor like this, or is it going to be steeper for some values like this, or is it going to be like, I wondered if it's going to be like something like this. Of course, this cannot be, this is, sorry about that, this cannot be, this is not even a single valued function, no. So let me get rid of that. Now the question I am trying to raise is, how is this shape going to change? And again, for this, we need to focus our attention on this phase function, which is 2 zeta omega upon omega n divided by 1 minus omega squared upon omega n squared. Now what I am saying is, suppose zeta is very small, right. So if zeta is very small, then how is this factor going to change? I mean, at the omega is equal to omega n point, how is this going to transition? So if zeta is very small, you notice that omega is equal to omega n is the critical point. If omega is slightly less than omega n, then this part is positive. If omega approaches omega n from the left, then 1 minus omega upon omega n, this term is greater than 0. If omega approaches omega n, note that because there is a discontinuity, these limits will not be equal. From the right, then 1 minus omega squared upon omega n squared is less than 0. That gives rise to this plus or minus 180 degrees after all. It becomes negative immediately, so the real part becomes negative. But what about the imaginary part? You see, the imaginary part is going to depend on this zeta, no? So what I am saying is that as you keep, okay, let me draw another figure here, and let me consider only for this case only this pole here, right. So this is the 0 degree line, and this is the minus 180 degree line, and let us say this is omega is equal to omega by omega n is equal to 1 here, yeah. So we notice that if we draw this line up until here, and then we draw this higher asymptote at this point, then clearly here is a discontinuity here, and at this point we know that it is going to be exactly equal to, we have seen that at omega is equal to omega n, this is minus 90 degrees, yeah. So we have this, but then how does it pass through this is our question. Does it go like this, or does it come very steep? Now here is where this zeta will play a crucial role. As you make zeta small, you see, even if omega by omega n is slightly less than 1 or slightly more than 1, it is a zeta value in the neighborhood of omega is equal to omega n, whether it is from the left side or right side, so either it is 0.99 or it is 1.01, ultimately this is going to be, this imaginary part is going to be exclusively, the magnitude of the imaginary part is exclusively going to be governed by zeta. So if zeta is very small, so if it is very lightly damped, this imaginary part is very small within a neighborhood of omega by omega n is equal to 1. So what does that mean? So then it means that this is going to be a very small quantity over a very small quantity. So probably they are going to be comparable. On the other hand, if zeta is reasonably large, yeah, if zeta is reasonably large, then what happens? You see, this quantity is very small, but this quantity is large, which means the imaginary part is large. Now think of a phasor. think of a phasor where both the imaginary and the real parts are very small. So, this is again a rough understanding of this. Yeah. So, then you have this angle could be a reasonable value here. On the other hand, if this imaginary part is very large, yeah, and the real part is very small, which is what happens in the proximity in the neighborhood of omega closing in on omega n, right. Then what happens? Then you see that if the imaginary part is, for example, very large, so for example somewhere here, and the real part is very small, or somewhere here, yeah. So, we have this, for example, the imaginary part is positive, so it is going to be somewhere here or here, and the real part is going to be negative. So, you see what is the transition for larger values of zeta, yeah, this function is going to transition from here to here, yeah. So, this phase change as omega transitions through this omega n from the left hand side and the right hand side is this much. So, what does that tell us? That tells us that there is a smoother change, isn't it, in the sense that you see this omega n by omega is close to unity, but slightly more. So, that means omega is slightly greater than unity. So, therefore, both the real part and the imaginary part are positive, but the real part is very small. And suddenly you transition and you make omega slightly more than omega n, and then this real imaginary part is still going to be very close, yeah, but the real part has now changed sign. So, the real part is now negative. So, you have transitioned from here to here, yeah. So, this is your phase change. So, there is a small change. So, for a small change in omega, there is a small change in the phase. So, it is more smooth, it is more continuous. On the other hand, if the zeta is very small, then for example, you are here and now you are here. So, you have made a larger transition, no? The delta theta is much larger. So, for a small change in omega, the change in theta is much larger, right. So, therefore, the steeper curve corresponds to zeta 1 and this smoother curve corresponds to zeta 2, where zeta 2 is greater than zeta 1. So, as you make zeta smaller and smaller, this almost becomes like a step jump or discontinuity, okay. So, to summarize, what we have seen is that as you draw the magnitude and the phase plot for this complex pole pair, so this is omega, this is 20 log m omega and this is phi omega. To summarize our discussions, what we have seen is that the magnitude function, of course, you draw this 40 dB per decade, this is minus 40 dB per decade, that is the asymptotic approximation. Of course, for this you draw this at 0 degrees and you draw this at minus 180 degrees and you draw this at 180 degrees. Let me erase that line, yeah. So, then you have this, so this is, yeah. So, to summarize, we have seen this is a quick asymptotic sketch of the phase and the magnitude. But now if you want to account for the zeta, then you will see that as you keep decreasing zeta, yeah, so for higher values of zeta this will almost be like a first order factor, except that this is 40 dB per decade instead of 20 dB per decade. But for as you keep decreasing zeta, yeah, what happens is that this resonant peak starts to increase. So, you will have some plot like this, or you will have some plot like this, yeah, and as you keep decreasing zeta, this resonant peak, I am sorry, so this actually what should happen is as zeta decreases, this peak value increases, and also you see that the peak shifts more, you know, where was the location of this peak? So, remember that the location of the peak was at omega n times 1 minus 2 zeta squared, yeah. So, then as you keep decreasing zeta, this omega n times square root of 1 minus 2 zeta squared shifts to the right. So, not only does this magnitude increase, but you see that as you keep decreasing zeta, it will take on some shape like this, of course not as bad as I have drawn it here, yeah, something like this, something like this. So, peak shifts right, yeah, and increases as zeta decreases. So, that is what we have seen here. For the phase plot on the other hand, what we have seen is that as you keep decreasing zeta, this becomes steeper and steeper. So, this is probably for a lower zeta, for a higher zeta, this is for a even, sorry, so this is probably for an even better damping, yeah. So, as zeta decreases, the steepness of phi omega increases, right. So, of course, I have drawn only the picture for the pole, you can analogously draw the picture for the 0, yeah. So, for example, in this case the 0 will be something like this, and then there will be something like this and something like this, yeah. So, that is going to be the pole and the 0. So, analogously here also you will have a very steep, or rather a rather steep rise here, an even steeper rise for a lesser zeta, and a rather smoothened rise for a higher value of zeta, okay. So, that is the summary of the second order block for you. So, in the next lecture we shall take up an example and hopefully clear this all up even further. We will take a proper transfer function, decompose it into its constituent blocks, draw the Bode plot for those constituent blocks, and then add them up together to get the overall Bode plot for the entire transfer function. Till then, thank you.